Hi everybody, we're starting a new chapter today, and today what we're going to be talking about are polynomial functions. This section I'm going to record a couple of screencasts for. So specifically in this screencast, we're going to identify a polynomial function, both looking at the graph and the equation, and we're going to determine the behavior of a polynomial function using the leading term test. Okay, so let's get started. So the first thing we want to do is talk about a polynomial function. Don't get freaked out by this, but this is the definition of a polynomial function. And I know you look at this equation and you think, holy crap, this is what I hate about math. But don't get upset. All this is saying is that a polynomial function is going to have exponents that are whole numbers and the coefficients are real numbers. So here are some examples of polynomial functions. This is what the equations look like. Notice we have real numbers for the coefficients. Notice that the exponents are all whole numbers. And this is what the graph of these polynomial functions look like. Okay, so now compare these to the graphs and equations of functions that are not polynomial functions. Here we have an absolute value. Here we have a square root. This is x to the 4/5, and this is a rational function. These are not polynomial functions. Let me go back to that previous examples. Okay, so let me show you a couple things. First of all these graphs are continuous. That means you can draw them without picking your pencil off the table. The domain of every one of these polynomial functions is all real numbers. That means every x value, it goes through every single x value. There are no sharp points on these graphs. There's no you'll see on the next screen what I'm talking about, but every time it changes from increasing to decreasing, it does that smoothly, not with a sharp change. And the exponents are all whole numbers, and there are no variables in any denominators. So looking at those polynomial functions that are not polynomial functions, you'll notice this example is not continuous. I'd have to pick my pencil up off the table to draw this. That's why this is not polynomial. The domain is not all real numbers. That happens here, and that happens here. There are sharp points on these two graphs, and there can't be sharp points for a polynomial function. The exponents are not all whole numbers. Here you have an example of an exponent that's not a whole number. And here we have an example of when we have a variable in the denominator. Okay, now going back to that definition of a polynomial function. What we want to focus on here is this term right here. That's the first term in this, because this is written in descending order, meaning that the highest exponent is first. So we call this term a sub n x to the n, and if you're wondering what I just said, it's a sub n times x to the n power. So a sub n x to the n is the leading term. A sub n, without the x to the n part, is the leading coefficient. And n is the degree of my polynomial. Let's look at a couple examples. So in this example, f of x equals 5. If we're going to try to determine the degree of that polynomial, you need to think of this expression, f of x equals 5, is the same as f of x equals 5 times x to the 0, because x to the 0 would be 1. So that's the same as f of x equals 5. So what is the degree of this polynomial function? Well, the degree is 0. That's the power on x. The leading term is 5x to the 0, and the leading coefficient is 5. Look at the next example. The degree of this function is 2. The leading term is negative 3x squared, and the leading coefficient is negative 3. See if you can do the next two. You can pause the screencast. Did you get a degree of 4 for this one? Be careful. The degree is the highest power in the function. Did you have a 4 there? The leading term is negative x to the 4th. See, the leading term is that term that has the highest exponent. So it's not necessarily the first one. You got to look at what's written and make sure you're using the highest degree. And the leading coefficient here is negative 1. For this expression, the highest power is 5, so that's the degree. That term that has 5 as the exponent is 1.1x to the 5th, so that's the leading term, and so the leading coefficient is 1.1. Okay, so I want to talk about this leading term test, and I want to lay some groundwork. So what I want you to do is I want you to graph these on your calculator. So pause the screencast and graph all of these on your calculator. You should have gotten these graphs. Y is equal to x, y equals x cubed, y equals x to the 5th, y equals x squared, and y equals x to the 4th. Do you see a pattern here? Could you make a prediction? Don't type this in your calculator yet. Can you guess what x to the 6th is going to look like based on what's happening here? So did you think it would look like this? Go ahead and graph it. Do you see a pattern here? With y equals x to the 3rd, y equals x to the 5th. Do you see how these are starting on the left and ending on the right? So bottom left to top right. Bottom left to top right. You could think of it as 3rd quadrant to 1st quadrant. 3rd quadrant to 1st quadrant. And then with x squared, x to the 4th, and x to the 6th, we are starting in the upper left and ending in the upper right. You could think of that as 2nd to 1st quadrants, right? Sort of like a U shape. Well, hopefully you can think about, all right, what would x to the 17th power look like? Well, 17 is an odd number, and it looks like when the exponents are odd, we have that bottom left to top right. So you would expect it to look like this. Okay, now what happens when the lead coefficient is negative? So explore this on your calculator. Type y equals negative x to the 3rd and y equals negative x to the 4th, and compare them to what you have for when the coefficient is positive. So as you should have expected, the graph is shifted, or reflected, I should say. It's reflected over that x-axis. So y equals x to the 3rd and y equals negative x to the 3rd. Only thing that happened is we flipped it, right? So if you put all this together, we can make predictions about what's happening with polynomial functions. And this predictions is called the leading term test. So when you take that leading term, n is the degree. So if the degree of the function is even, we basically have a U-ish kind of shape. If the leading coefficient is positive, that U is going to be facing up. And if the leading coefficient, a sub n, is negative, the U is going to be upside down. When the degree is odd, we have bottom left, top right when the leading coefficient is positive, and top left to bottom right when that leading coefficient is negative. Okay, so let's look at some examples. Oh, by the way, this little squiggly line is we're going to have more complicated functions. We're not going to have just y equals x squared or y equals x to the fifth. There's going to be numbers in the middle. So we can't really predict how many tops and bottoms, peaks and valleys, max and mins, if you will, there's going to be in the middle. We can only predict what's going to happen at the very beginning and the very end of our graph. So let's look at an example. So f of x is equal to 3x to the fourth minus 2x cubed plus 3. So to figure out using this leading term test, which of these terms is the leading term? And then figure out the leading coefficient and the degree. Well, the leading term is 3x to the fourth. The leading coefficient is positive 3. And the degree is 4. So a sub n is positive because it's positive 3. The degree is even. So we expect the graph to have this general shape, this U-ish kind of shape. And this is indeed the graph of that function. Hope that's making sense. Let's look at another example. So in my next example, we have negative 5x to the third minus x squared plus 4x plus 2. Which is the leading term, and then determine the leading coefficient, determine the degree, and figure out which of these you think that is accurate for this graph. The leading term is negative 5x to the third. The leading coefficient is negative 5. And the degree is even. It's 3. So if it's odd. It's 3, so it's odd. Duh. So if the degree is odd and the leading coefficient is negative, we have this graph right here. So you can see that this is actually the graph of this function. So this is what I'm talking about. We don't really know if it comes up and comes back down. All we know is it starts at the top left and ends at the bottom right. It has this general shape, and something else might be happening inside here. Okay? All right, let's see what you've learned. So in this last screen, here's a question that I took from your textbook. You might also see this in your homework. So use the leading term test to match one of these functions with the equation on the right. So these are the graphs of the functions. These are the equations. So what you're going to be using is this leading term test. All right? So let's look at this first graph. What could this be the graph of? Could it be number 19? No, it can't be, because this is definitely the graph of an odd function. So that eliminates 19, that eliminates 20, maybe 21 and 22. So how do you determine which one of these it would be? Well, because of the shape. If this shape is starting in the top left and ending in the top right, bottom right, that means it has to be odd, and the leading coefficient has to be negative. So the only number it could be, the only equation, is number 22. All right, how about letter B? It's even and positive. The leading coefficient's positive. So that should be equation number 20. Letter C, it's even and the leading coefficient is negative because of the shape. So it should be number 19. And lastly, letter D, it's positive because of the shape, and the degree has to be odd because of the shape. Remember, it looks like this. So odd and positive means it's number 21. All right, I hope you learned something new. I hope this helps you with your homework. Email me if you have any questions whatsoever.